Hi, I'm Edana Sutherland, an MSc research student in Geography and Earth Sciences, working with lecturer Iain Neill on deep geothermal potential in Highland Scotland. I'm here to briefly present some ongoing work on Scotland's geological history and introduce some projects, including my own. The UK energy transition is shifting power generation from urban centres to rural areas, especially through wind and pump storage projects. Through community engagement, Iain has identified landowners and enterprise organisations who are open to deep geothermal heating. They're attracted by its low visual impact and potential for community ownership. They're keen to know if geological conditions and the price could ever be right, and it's vital that geologists are ready with the information on the nation's potential. So before moving to Scotland, in Ireland, a nationwide geophysical survey has been combined with existing radiogenic heat production, thermal conductivity and heat capacity data. The result is a series of subsurface temperature maps showing very favourable temperature conditions at modest crustal depths, with temperatures at around 5 kilometres depth exceeding 150 degrees Celsius, particularly in Ulster, Donegal and Mayo, areas that are analogous in their geological structure to Scotland and where geothermal for heat and power is highly plausible. In Scotland, our deep geothermal potential is not fully mapped out. We understand that some granite bodies have naturally high radiogenic heat production and are therefore potential targets, but their origin and their buried extent are not well known. But this rock property data can be rapidly built on as the Thermal Cal project progresses. Deep fault zones themselves may be potential geothermal targets, so an understanding of their overall structure and their history of past fluid flow will be part of my own research, focused on the Great Glen Fault. Iain is also involved in efforts to secure funding for passive seismic experiments to better understand our subsurface. So moving on to geology, Scotland is made up of blocks of crust amalgamated during continental collisions in the Paleozoic, specifically the Caledonian and the Acadian orogenies. These events were accompanied by magmatism. Some magmas, especially those from melting of ancient sedimentary rocks, can be enriched in isotopes of uranium, thorium and potassium, leading to high heat production. Knowing when in the orogenic cycle these granites form, their chemistry and where sediments from their erosion travel to can significantly enhance geothermal exploration. Additionally, the Great Glen Fault cuts through the whole thickness of the Scottish crust, and due to repeated reactivation in the last 400 million years, it may be a relatively permeable structure of interest. Until recently, we had little systematic understanding of the low and high heat producing Paleozoic intrusions of Scotland. From the 1980s onwards, they were often called newer granites, despite being neither new in the orogenic cycle, many of them even being granite in a petrological or geochemical sense. In the past few years, however, here in Glasgow and at the BGS, dating and redating intrusions has amounted to 15 bodies so far. Combined with improved geological models of the UK, we should be able to produce a modern plate tectonic understanding of the origins of these intrusions. So this geological reconstruction shows Paleozoic subduction and collision events. Magmatism early in the orogenic cycle is proposed to be driven by subduction and slab rollback, leading to mantle melting, largely restricted to the Grampian and Northern Highlands. But around 424 million years ago, Scotland and Northern England experienced a major increase in mantle-derived magmatism. This resulted in widespread emplacement of mafic to felsic intrusions driven by lithospheric delamination, slab breakoff, and the initiation of the new Acadian subduction. Again, most bodies of this age are derived from partial melting of the mantle. Only a few million years later, however, there's a final pulse of magmatism in the Northern Highlands, this time dominated by crustal melting, attributed to decompression at the end of a cycle of collisional tectonics. This process continues and occurs later in the Grampian Highlands and the Southern Uplands. So in the Northern Highlands, the distinction between mantle-derived and crustal-derived intrusions is quite stark. The earlier bodies are mostly grey granodiorite, and their chemistry and zircon loads indicate derivation from melting of the upper mantle with low crustal involvement. And these bodies are ubiquitously low in potassium, uranium and thorium and have low radiogenic heat production. By contrast, the youngest intrusions at around 418 million years ago are archetypal granites. They're red in colour, chemically highly evolved, and they have few mafic minerals. Their chemistry and zircons strongly indicate a crustal source of magmatism, with these bodies having moderate to high heat production characteristics. Elsewhere in Scotland, this mantle-derived magmatism is also interrupted by short bursts of crustal melting. In the Grampian Highlands, the emplacement at current erosion levels occurred from 432 to 390 million years ago, with the high heat granites restricted to 409 to 404 million years ago. And in the southern uplands, emplacement lasted from about 416 to 395, including the moderately high heat Cheviot granite at about 400 million years ago. So refining the geological record and its geodynamic interpretation are essential, as is locating buried granites of a similar age that may have a thermally insulating blanket of sedimentary rock. Dating and geochemistry can provide information on whether more high heat granites exist at depth in regions like the Midland Valley, Orkney, Caithness and Easter Ross. BSc student Fern Cameron in Geography and Earth Sciences is compiling geochemical data to estimate radiogenic heat production in the Grampian Highlands. Many older data sets lack full measurements because uranium and thorium weren't routinely analysed before the 1980s. So Fern's going to establish minimum heat production values as well as possible low certainty values where there are partial data. And they'll also highlight data poor regions which should be targeted in future, including via thermal-cal. And just a note that existing borehole data have produced a heat flow map in Scotland that shows virtually no relationship to the underlying geology, which is unlike regions such as Cornwall or Weardale. This reinforces the need to generate accurate, widespread geological data. In my own project, I'll be looking at the Great Glen Fault and Easter Ross, looking at past fluid flow through local rocks, as well as generating new heat production data via portable gamma ray spectrometry. These data may be helpful for thermal-cal, and I also intend to work with computational geoscience PhD student Lucy Heaney to build models of 2D heat flow beneath specific areas of interest. Lucy created a 5x5 model of conductive heat flow beneath Kinlochbervie in the Northwest Highlands for her MSc dissertation. And she now hopes to integrate my new data to build a more realistic advective heat flow model for my field sites later in 2026. In summary, we want to refine the geodynamic story of Scotland and the wider British Isles, so we know where the most promising rocks for geothermal resources actually are. Geophysical data will be central to that and can in turn be integrated with new results from the thermal-cal project. But we also need to remember the human dimension, that community-owned geothermal heat has a real appeal, especially in highland communities, and that's the key driver for this work. Thank you for listening.